So our next speaker is Fernando Lucatelli Nunes from the University of Coimbra, and the title of the talk is A Generalization of the Eilenberg-Moore Factorization. Please, Fernando.
Thank you so much. Thank you for this invitation. I really enjoyed attending the other talks. They were very interesting. It's funny how I think three of them are more or less connected, although maybe a bit loosely to mine. So it is very nice session. Thank you. Um, and well, I'm going to talk about this generalization of the Eilenberg-Moore factorization. This is kind of an old work. I don't have many answers. Oh, I have more questions. I hope you enjoy having questions. I will just present my formal result, and then you're going to see that there are many questions, in particular about examples, but also a characterization theorem. Yeah. So what I intend to talk here is just, let's check if this system works well firstly. Yeah, it's going to be a little bit slow, but it should work. So I'm going to I am generally interested in low and higher dimensional categorical structures, but I'm just going to talk about monads and monadicity. So it's a very less specific. I think it should be maybe one of the topics that every category theorist has some interest at least. And
Sorry, Fernando, just a moment. On the right, I can see a menu open. Can you just close
oh,
that?
thank you. Maybe I can also, is this possible to take this off? Yeah. Okay, it's fine. Thank you. Yeah, so monads and monadicity, the original result was um inside a two category with just enough two-dimensional limits and such. The funny thing is that it brings something new even for the usual two category of categories. The main point was to kind of understand formally monadicity in a two category. I decided to add this comment since Enrico is the chairman. This is I actually did did this work in 2018, although it was published way later. And it was my main observation was in my stay in Louvain-la-Neuve, which was very pleasant. Stayed there with Maria Manuel and Walter Toll, and there were many people there in that moment. Um, so, uh, yeah, so the aim of the talk is I'm not going to go into details, the technical details, and I'm not going to talk about general aspects or general directions towards this resulting uh, general two category. I'm just going to try to sketch consequences in the two category of categories. So of course, categories, functors, and natural transformations. And well, I call it this factorization, if I'm not mistaken. Originally, I called like a semantic factorization of a functor, or this semantic descent factorization of a functor, or of a morphism in the two category. But many people fought with the um, terminology, and also I realized with time that whenever I say descent, people get away and scared. So I want to just make this kind of a um, comparison with this. We can think about this factorization as a lax version of a regular image factorization, and you're going to see that's precisely the case. As long as we add particular coherences, then these coherences give rise to descent stuff. So what I'm going to show that Eilenberg-Moore and co-Eilenberg-Moore arise naturally as examples of this factorization. So it's kind of a factorization of a functor that, in the case that Eilenberg-Moore or co-Eilenberg-Moore factorizations make sense, they they coincide with the factorization. And dually, we have the Kleisli and the co-Kleisli. The dual, I'm not going to talk much about it. If you have questions in the end, you can ask. But they're kind of more trivial, so that's why because Kleisli factorization is just part of the factorization system, bijective on objects and fully faithful. So yeah, so it's a bit easier to understand. And then again, I'm just saying that this actually is going to generalize Eilenberg-Moore, co-Eilenberg-Moore, and they're actually the same. So it's like a common generalization of Eilenberg-Moore and co-Eilenberg-Moore. It's not like I'm going to dualize to get co-Eilenberg-Moore. So if we start with a functor and you have a joint situation, so this is kind of a regular one-dimensional category theory. You have two things, one monad and one comonad induced, and then because of this monad and comonad, you have what I'm calling Eilenberg-Moore factorization, which is just the factorizations induced by the universal property of the category of algebras and the category of coalgebras, with the right and left adjoints respectively. And it was this paper by Eilenberg-Moore in 1965. And it's very nice to revisit, by the way, this paper. I think they have many nice things there that are sometimes, at least in textbooks, they are overlooked. And then we have examples, and this example is very interesting, and I showed this example just predicting one possible question in the future, which is you have a free category, free groups, and in the category of groups, and then you have the adjunction, you have the Eilenberg-Moore factorization, the logical spaces, and forgetful, you also have a left adjoint, you have factorization. Compact Hausdorff for set. It's also monadic, right? So it's also something that I want to talk about, which is kind of, okay, what would be the notion of monadic in our setting. And abelian groups also, but then not monadic. Okay, this is just a short recall. And this is the example that I wanted to talk about, which is, in case we have a question in the future, which is showing that composition of monadic functors is not monadic. So you have here two monadic functors, this one, which is the forgetful functor between torsion, free abelian groups, and set. And this is also monadic, forgetful functor between the category of abelian groups and set. But sorry, this is monadic, and this is not monadic, right? But this is not monadic. So we have composition of two monadic functors, and they are not monadic. Okay. The next example is just to talk about like comparing Eilenberg-Moore and co-Eilenberg-Moore factorization. So you haven't thought about this before. So if you start, for instance, the category, this is a concrete example, but then we talk about the general thing, which is if you start with a category of small diagrams in a category C, and you forget to the corresponding discrete diagram, this is going to have left or right adjoints if C is complete and complete, and it's going to be monadic and comonadic. And indeed, what happens is that when you have an adjunction like this, so it's a three, like a G is left adjoint to F, but it's also right adjoint to some U. Then the co-Eilenberg-Moore and the Eilenberg-Moore categories of the corresponding monad, like monad for this one and comonad for this one, they are actually equivalent, which shows that the factorization of G, the co-Eilenberg-Moore and the Eilenberg-Moore factorization, they are actually equivalent. So they're basically the same. So getting back to the general setting, okay, if you start with a functor, G, you cannot have a Eilenberg-Moore factorization because Eilenberg-Moore factorization require at least if you either a left adjoint or at least a condensed monad or something a bit slightly more general than that. But usually the setting that people are usually familiar with is when G has a condensed monad. But if you are not familiar with condensed monad, at least you can think if G has a left adjoint. There is no Eilenberg-Moore factorization in this setting. So we can take a look at the set, category of set instead of the two category of categories. And remember that if you have a function, you can consider the co-kernel pair of G, and then where this part is the push out of G along G, and or the kernel pair, and then with the equalizer here, you get the regular image factorization, and with the co-equalizer, you have the dual. Right? So we have a less regular image factorization of a function in set. And then we bring together to the case, firstly, we observe that this is, of course, possible in any category C with co-equalizers and co-kernel pairs, right? Co-kernel pair here being push out of G along G. And we bring back to the setting of categories. So we also have this factorization in the two category of categories. But I don't want to talk about this in particular. We want to adapt this to the two-dimensional setting and take a bit of exploit the fact that we have a two-dimensional structure in the two category of categories. And first thing to consider to be lax, it would be like instead of considering equalizer, maybe you want to consider inserter, right? And then, but before that, we can also change what we mean by co-kernel pair of G. And this is a common structure, and I'll tell you why it's common. It had been already considered, but the dual one, which is what I call two-dimensional co-kernel diagram. And two-dimensional co-kernel diagram, we replace the push out of G along G with the opcomma object of G along G. And I would say what is the opcomma, but and then we do the triple here, which will also try to show you better what it is. And we have induced morphisms, as in the case of the co-kernel pair, which are induced by universal properties of these constructions. And this has been, or had been, considered, but the dual one, so maybe you are familiar with the dual one, and again, they also have different names, and there is also some fight about terminology, which I'm okay with any terminology, but which is the kernel diagram, two-dimensional kernel diagram, which again you can call something else. So you might find this this construction in the literature, which is where here is just the comma category. Okay, so the comma category of G along G. So this is just GG in cat, right? And this is also, yeah, I'll tell you more about this afterwards. But then this construction has been studied in literature, for instance, by Rose Street and Steve Lack, and even John Burke probably has something. And one thing that is known about this, besides some other aspects of that, is that this is, and I'll tell you more about later, but if you have if you take a specific co-limit, two-dimensional co-limit here, this is going to induce precisely the, like, after equivalence, the fully faithful bijective of an object. If it is strict to limit, then it's not up to the equivalence, but it's a morphism. Bijective of an object and fully faithful factorization of the functor G. Okay. And what I'm doing is just taking what is supposed to be the dual notion of that. So this is not taken from just a guess. It's just because people has been studying that, including for trying to develop higher dimensional notions of exact two categories, and like, I think in the work by Richard Gardner and such. So yeah, so we consider the dual, and we start to study that, right? Because once you study the limit version, you can really have a better notion, because then if you know in cat the limit version, you can get results for the co-limit and and for the limit in a two category by representability, right? So yeah, so again, this is the opcomma category. So the opcomma category is basically the category that has the universal property that's dual for the comma. So if you start like, sorry. So if you start with A, B, these are functors, and then you have a C here, and here is J, H, and you have a choose cell. You want to have this, of course, there is another. So this plus something more, right? On the choose cell level, but then the one cell level is basically you have this morphisms, have this one that is, sorry, the other way around, which is universal. And if you have an alpha and H, you want to induce a unique functor here, H prime, such that this base is equal to this alpha. And of course, you have to also put the true cell level of this universal property. That is precisely the dual universal property of the comma. And you can write in cat as a canonical colimit. So you start with G here, and here this two is a category 0 to 1. There's two objects, 0 and 1, and only one morphism. And then I0 is just the inclusion in 0. So this is taking X to X0. And the other one is taking Y to Y to Y1. Okay. And then take this conical colimit in the two category of categories. And this is precisely the opcomma. So invited to try to understand this. Yeah, we can talk about this later, but yeah, let's for now just accept that this can be done, and then this one can be written as this there's this conical co-limit. So this third one is this conical co-limit, again, including 0, including 1, and here including 3. And then you just take this conical co-limit, and then you have this third one. So it's like the idea would be, this is precisely like, at least the previous one, this is precisely like what you expect to be the lax version of pushout, right? Pushout you were gluing, but here you add freely morphisms between the things that are equal, that are taken from equal things. Okay, so once you accept this, and this is the kind of hard part, then you can take the so-called descent category, which is a two-dimensional limit again. And this two-dimensional limit is, if you call D0, D1, here, there's morphisms. So descent, the objects are going to be pairs, where so objects of this category are going to be pairs, where X, so let me put pairs, X, D0, X to D1, X, pairs when X is an object of B, and alpha is a morphism of B. And then plus coherence conditions, So, okay. And so S0 alpha identity and such. Plus and I can write B0, B1, B2, B2 alpha composed of B1 alpha is equal to B0, something like this. And sometimes I try some more. So this case is strict. Okay, so then you have a two-dimensional limit, and indeed, this two-dimensional limit, as it goes, it has a universal property, which is descent of HG B. So there is this functor that forgets to B. And then if you put D0, D1 and D0, then and you have an alpha universal two cell here. This universal two cell satisfies the coherence conditions, which is this identity and this other one that we call associativity. And the universal property basically says that if H, if you give another category, in this case A, and a functor G, and you give a two cell alpha between D0G and D1G, or D1G and D0G, and with the coherence conditions, then you have induced morphism. And in this case, we indeed can get the induced morphism because we are going to be able to precisely give such an alpha satisfying the coherence conditions via the construction here of the opcomma category. And then you have a normal comparison, and this is a factorization of any functor G, because cat always has descent categories, there's descent objects. It's a two-dimensional limit that cat has all two-dimensional limits, and also always have opcomma objects. Cat has opcomma categories. So this is why this is similar, or like a two-dimensional version of the usual regular the regular image factorization, because you have a notion of what is a two-dimensional cokernel diagram instead of a cokernel pair, and you take the descent category or descent object instead of equalizer. And yeah, and the great thing is that every functor G has this factorization, okay? But not only that, the formal result that I wanted to show is precisely that this generalizes the Eilenberg-Moore factorization in the sense that if G has a right adjoint, then this factorization coincides with the co-Eilenberg-Moore factorization. And if G has a left adjoint, then it coincides with the Eilenberg-Moore factorization. In particular, as Eilenberg-Moore already knew, if G has a left and a right adjoint, this factorization coincides with both, right? Eilenberg-Moore and Eilenberg-Moore factorization. And so this shows how this is a common generalization of the Eilenberg-Moore factorization. But cookie is that actually, although I only phrase this in terms of left and right adjoint, actually, if you have G has only a codensity monad, so if you have worked of codensity monad plus a small technical condition, then indeed still this factorization didn't generalize the Eilenberg-Moore factorization. So it's kind of an exact condition that underlies the Eilenberg-Moore and Eilenberg-Moore factorization, and kind of show how like descent data, when I say descent data, I'm precisely talking about this category here of this two-dimensional kernel diagram, generalize algebraic and coalgebraic structures, right? In the sense of monads and comonads. So the question that I open, and that's something that as I said, know that there are plenty of questions, firstly examples, and I will not going to be able to provide you with many. And the second question is probably if this is a part of a factorization system, and I am not sure that it's not, and I had thought about that, and I think I proved it was not, but you are invited to try. And other question is this one. So if you start with a functor G and do this construction and this factorization, you're going to have certain functors G where this comparison is an equivalence. And I call this effective faithful functors, morphisms or functors. And for the case of Eilenberg-Moore, we have the monadicity theorem. So the question is, what are the functors that are effective or faithful functors? This is still open. And as I showed, like effective faithful plus left adjoint should imply monadic, but not only imply, is if and only if, and it's in any two category. Any two category with the descent objects of two-dimensional cokernel diagrams, assuming that also the two category provides you opcomma objects, allowing you to construct two-dimensional cokernel diagrams. So yeah, so this gives a formal theorem for two categories, and yeah, that's the questions. And if you want a glimpse of what one can do, is I didn't complete this here because I was about to check, but one thing that I think one can easily prove is that if X and Y are thin categories, then being effective or faithful functor is precisely equivalent to be a Laxet morphism. But this certainly is not true for more general study. So thank you.
Thank you very much, Fernando, for your talk. Questions or comments? Okay, please.
Can I ask a question, Enrico?
Yes, please.
It's actually a comment. So thank you very much, Fernando. I find this result very impressive that you can recover algebras and coalgebras this way. But it seems like we have to wait for 63 years before we find the result. Or was the date, because I thought I read that the result was proved in 2089. Or did I misread it?
No, it's 2018.
18, okay, great. And do you know what happens in other two categories?
Well, the result is very formal. So every two category of two-dimensional.
I know, but the other interesting examples where
locally
here's something there.
Locally ordered two categories. Should be simple. Should be equivalent to X morphisms. The effective morphisms. Effective faithful morphisms. But otherwise, no, there isn't any. I think there is one paper I can send you later. That was a long time ago, and the author didn't know that would coincide with the Eilenberg-Moore general factorization, but the author studied this factorization in a specific two category. But besides,
so what happens for? Oh, sorry.
Go ahead.
What happens, for example, if we take the category of functors, so the category of arrows of cat? Do you know what happens there?
Yes, but what do you mean by what happens?
What does the construction give? And is it component-wise or?
It is, because it's a limit and co-limit.
It is component-wise. Okay. Okay.
Yeah.
All right. Okay. Thank you very much.
Thank you, Zurab. Any other question? If not, I have one, just to be sure to understand what you said about the factorization system. Fernando, when you say that it is not part of a factorization system, you mean in a factorization system in a one-dimensional sense or in a two-dimensional sense?
Both.
Okay. Thank you.
But I mean, as I said, I had been people made this question a long time ago, and I looked into it, and I remember I proved it. That was not. And I don't have the proof, so I invite people to look into that if they're really, really interested in checking, because I might be mistaken. But otherwise, I suspect that most of the notions that we have will fail. So if it's just up to isomorphism or something like up to equivalence, it will fail. I expect that if there is such a notion of factorization system, it will be a different one, right? Because it should include Eilenberg-Moore factorization there.
Mm-hmm. Because what I expect is that at least in some cases it could be. I have in mind in a situation which is quite special when you take symmetric two groups, and in this case it is a factorization system, but in a two-dimensional sense, not in a one-dimensional sense.
Yeah, it can be. It can be in specific two categories. It can be, I'm just saying, a cat. Mm-hmm. But in specific two categories, should be even like in a locally ordered two category, it should be.
Okay, thank you very much. If there are no other questions, I suggest we thank again Fernando, but also Cipriano